Next concept is sharing bridge arrangement in the case of grounded capacitors. So for the safety reason, the shield potential with respect to each other, one of the terminal of the bridge is earthed. So this is generally it is of the low voltage arm of the connections of the supply source. So this is what we discussed in the previous conditions. Because the low voltage impedance arm with respect to the detector branch will gives an high signal to the noise ratio for the measurement. While testing ground test objects like underground cables or the bushings with the flange grounded to the tank of the transformer, one of the detectors, that is E or F, has to be grounded. So which is shown here, this is the one and this is the another one. These two are the bridges which is adopted for the measurement. So in the case of inverted bridge operation, a self-contained bridge is located inside the Faraday case at the high voltage terminal, and there is a standard capacitor which is mounted on the insulating support generally. So the variable arm are operated by insulated isolating rods. Sometimes there is an operator himself who will be inside the Faraday case. So in the case of the grounded detector arrangement, stray capacitance of the high voltage terminal, that is nothing but CG, and of the source lead etc. This is come in parallel with the test object, okay, which you can see here, CG and this CX, which is come in parallel. So hence the balancing is to be done in the two steps. The first step is the disconnection of the capacitance CG, and there is a measurement of tan delta. Then the test object is connected and there is a new balance is got. So there is a second balance which you can write it as Cx dash is equal to Cx plus Cg. Then we can able to calculate there is a tan delta loss angle measurement will gives rise to a parallel combination after doing simplification, Cx tan delta x plus Cg tan delta divided by Cx plus Cg. So hence there is an actual capacitance and the dissipation factor of the test object, which can be written as Cx is equal to Cx dash minus Cg. So this will gives rise to the equation tan delta x. This is the final one. Hence the accuracy of the measurement is poor if the grounded capacitance is large compared to that the test object capacitance. So the care has to be taken. This is the sharing bridge for the grounded capacitance, and this is the inverted one. So which you can see, this is the parallel combination. So with inserting and without inserting, we will get the balance equation, and we are going to find out. The next one is the sharing bridges in the case of high charging current. So there is some test object like high voltage power cables and power factor correction capacitor, which takes an very high charging current which may be exceeding the range of the variable resistance R4, that is nothing but the standard value of the resistance, which you can see here, the R4, this is R3 and the C3, and this is the standard value capacitance, and we don't have option to change this. Can, however, this having the value of the variable um, value of the capacitance and the resistance, and also we are keeping it as a constant. So further value of the resistance R4, this is the R4, will become so low that the contact resistance and the residual inductance can no longer be neglected. So this means that because it is subjected to the high current, so hence if we have a very high value of the resistance, so there is a inductance also, a charge inductance, that's nothing but residual inductance is also come into the picture. So for these conditions, the range can be increased by connecting the value of RS. So you can see here RS, which is in parallel with the R4. So for the objective like a power cables and high charging current devices. So under this, the balance condition, which is modified as, okay, after doing the final application by this is whatever the this into this divided by this into this, so I will get the balanced equation. At this point, Cx is equal to C2 R4 multiplied by Rs plus R small r plus S plus R4 divided by Rs R plus delta S. So where Rs is nothing but the shunt resistance, S is nothing but the slide wire, which you can see here, slide wire. It is a variable one, and delta S is nothing but a tabbed portion of the slide wire, because this is a small change in the values, and R is nothing but a fixed small resistance here. R4 is a decayed resistance box. So usually RS, this is nothing but the shunt value of the resistance, which is kept outside, and there is a special arrangement or made for the correction of its inductive phase angle error if necessary. Next concept is Schering-Bridge for high dissipation factors. So the extension of the ranges of the dissipation factor can be achieved by connecting in parallel an additional large capacitance C3. So this is what we have, the known value, standard, and R4, C3, and the R3. But to avoid expensive and large side decayed capacitances, the C3 R3 arm, which is modified, just you can see here. So this is not only C3 and R3 which is come in parallel, but R3 is made as slide wire along with the decayed resistance, and C3 is extended by connecting a single fixed capacitor. Okay, C3 and R3. R3 is made as slide wire, okay, varies from a minimum to the maximum value, and C3 is extended by connecting a single fixed capacitors. So usually by doing this modification, which is limited to tan delta, there's nothing but the loss angle factor, tan delta is equal to 1. So whereas in case of tan delta, which is greater than 1, and in the range from 1 to 10, or sometimes it is greater, the what is the arrangement, the R3 and C3, the slide wire what we used. So this is no longer made as a parallel combination. So instead this, what we are doing is connecting as a series R3 and C3, but this makes the test object to be equal to Cx, so which is in parallel with Rx. It means that, so in place of this R3 and R3 which is making in parallel, so we are making this Rx and the Cx which is connected in parallel. So this is makes that because under this condition, so we know that our opposite arms, okay, this and this and this multiplied this is equal to this and this, okay, Cs and R4 multiplied is equal to Cx Rx and the R3 and the C3 value. So this makes that test object which is in parallel with Rx value. So better approximate for the capacitance and the dielectrics. So with this modification, so tan delta range is made wider, which is varies from 10 to the power of minus 4 to the values even greater than the 10. So this arrangement what we shown here for 1 to 10, and this is for 1, means for the loss angle measurement. Audio frequency measurement techniques. So the basic bridge arrangement what we discussed in the previous condition, which may be used in the audio frequency ranges for the dielectric measurement, but it present problems at higher frequencies. Means for the higher frequency ranges, the value of R3 and C3 had to be altered. So sometimes balancing also becomes difficult for lower values of the test specimen, and the errors due to the stray capacitance across the R4 may be introduced. So therefore, in the case of a small capacitance measurement like 1 to 100 picofarad and less than that, so substitution method are used. So with this, the capacitance range may be more accurate. So also, in order to take care of all these effects, so there is an modified Schering-Bridge arrangement, what we can see here in this figure. So that is nothing but this is the bridge for the audio frequency ranges from a 50 hertz to 100 kilohertz. So the capacitance which is used for the dielectric measurement, what we shown here. So where this CA and RA and CB and RB are the ratio arm capacitances. There is a substitution method is preferred in this range for the greater accuracy. So this is what the sentence what I made here. The specimen which is connected across the standard variable capacitance, that is nothing but the Cn. Here what you can see, the bridge is said to be balanced with and without the dielectric specimen, that is Cx. Then the specimen capacitance connected to the Cx is the differentiation of the two readings of the standard capacitance Cn. Okay, that is nothing but Cx is equal to delta Cn, Cn dash minus Cn. So actually the balance for the loss factor which is done in, there are the three different ways of doing it. So that is nothing but the first one is a small variable resistance in series with the standard capacitance C1. Sorry, it is a Cn. So there is nothing but there are three ways. In that first one, there is small resistance which is in series with the standard capacitance Cn. Another method is there is a variable resistance, the value of high value, which is in parallel with the Cs. So here parallel to Cs value. Another method is there is a variable capacitor which is in parallel with Rb. Okay, this is what the Cb and the Rb. So this is the balanced equation. So these are the three conditions what I explained here. Okay, small resistance Cn and Cs and the Rb. So among these three, the third method, that is nothing but the variable capacitance which is in parallel with Rb. So it can be made variable capacitor of the high quality, and the errors that arises within the resistance at the high frequency can be avoided with the help of the third method. So then the dissipation factor, that's nothing but tan delta for the third method, which is given as tan delta is equal to C n dash by delta C into delta D. Okay, where delta D is equal to D minus D, that's nothing but omega RB CV minus CB dash. So usually the total capacitance Cn in the variable arm, which is made small to get the large value of the variation in delta D. So whenever the specimen capacitance, which is greater than that of the maximum value of the Cn, then the substitution method is not possible. So in that cases, we are going with the direct measurement without the value of the Cn is done. So for this condition, that's nothing but the case of direct measurement for Cx and delta can be written as Cx is equal to Rb by Ra into Cn. So resulting in tan delta is equal to F by F naught into Rb and the Cb. So this is made F by F naught into X. This is the dial reading, where we are considering that this is the F naught is equal, F naught is the calibration frequency. The range of this bridge can be extended from 1 picofarad to of around 1000 picofarad when the substitution method is used, from 1000 picofarad to 100 nanofarad, whereas in case of the direct method which is used. Transformer ratio or bridges. So it is a common practice used as a 4-arm Wheatstone bridge for the measurement of AC. So in high frequency measurement, the arms with high values of the resistance is difficult due to their residual inductance, skin effect, and also the capacitances. Also, the shielding and grounding it is becomes difficult in the case of large arms. So hence, the high frequency, the transformer arm bridge, which eliminates at least two of the arms which are preferred. So these bridges are also useful for the measurement of low value of the capacitance accurately. So here this is the circuit diagram. The ratio or bridges can be either voltage ratio type or the current ratio type. The former being which is used for high frequency low voltage applications. This is the schematic representation of the two arm ratio bridges. So assuming that under ideal condition for the null indication, so Vs by Vx is equal to Ns by Nx, that's equal to Cx by Cx, and Rx is equal to Rx by Ra is equal to Nx by Na. So where this x value, Cx and Cs are known as unknown and the standard value of the capacitances. Okay, Cx and Cs, this is unknown and the standard value, and this is Rx is known as unknown, and this is Ra is known as the standard resistance, and Nx is equal to the terms of unknown values, and Na is the standard, and Ns is the standard value of the number of the turns. So this is a schematic representation. So in practical transformers, the voltage ratio, it may be slightly differs from the turns ratio due to that no loading magnetizing current, and is also affected by the load current which is flowing into the circuit. So therefore the balancing condition which is shown, which involves there is an error. So The errors are classified as ratio and the loading errors and are determined separately and compensated in the construction. A practical bridge which is consisting by a general radio company so has a useful range from a fraction of 1 picofarad to around 100 microfarad and which covers a wide range of the frequency ranges from 100 hertz to 100 kilohertz. So the accuracy which is considered as better than 0.5 percentage. So this is how we are going to consider under the balanced condition. For high voltage application, so we need a sensitive measurement at a fixed frequency which is required. So the current comparator or the current ratio method which is used generally. So this is, we can see to that this is a 2 bits having CS and this G value and NX NA with a small modification here. So this bridge has advantages that the full voltage which is applied across the test capacitor CX, but also it has the drawbacks that a standard conductance GX value has to be built for high voltages. So it is very difficult to construct a precision conductance for the high voltage operations. So this limitation can be overcome by, and this is a new one, the modified one. So here there is the generating a low voltage signals, that is nothing but EF, which you can see here, EF, which is proportional and in phase with the supply E. Okay, across this point, this is a comparator EF and the E value. EF which is proportional and in phase with the supply E as shown in the figure here. So at balance there is no voltage across the current comparator. So if the gain of the amplifier is high, then the equation can be written EF is equal to CS by CF into E. So the balance equation of this bridge can be written as Cx is equal to modification Cs Ns by Nx and the conductance value Cs by Cf Ne by Nx into Ga. So the tan delta loss angle, so we'll give Gx by omega Cx value. So these are the things which is modified and defined in the case of earlier, and where Gx and Ga are known as unknown and standard value of the conductance, and Cf is nothing but Cf is a balancing capacitors. So this is the new way of the 2 arm bridges by replacing the 4 arm bridges.